Hello Science Alliance! This lesson is on terminal velocity. It's one of my favourite subjects, but it is also one of the subjects that I find hardest in physics. So if you listen to my explanations and you think, I don't get it, that's totally fine. It's perfectly normal. There are websites that you might have to stare at for a long time to really fully understand the concepts we talk about today, but that's fine. I've stared at the same websites. I'll send you the link. Not the most gripping start, but what I want to do first of all is to just look at a couple of equations that we have looked at in previous lessons. Alright, so hopefully, if you've seen the past 6 lessons, you're looking at these and recognising them. So the first one is F equals ma, classic, Newton's second law, force equals mass times acceleration. And the second one is one that we looked at last week, weight equals mass times gravitational field strength. You remember what gravitational field strength is? So Earth has got a gravitational field, as has everything that has mass. Everything's got a gravitational field. We said that the value of Earth's gravitational field was 10 newtons per kilogram. Let's rearrange these equations because this isn't actually the most helpful form of these equations. Here we go. So this is exactly the same equations, just rearranged. Weight is a force. So aren't these two just saying the same thing? Well, yes, they are actually. These two equations are kind of the same. It's a bit weird, but gravitational field strength on Earth can also be called the acceleration due to gravity. How much something is accelerated towards Earth, which kind of makes sense, right? Like if someone placed you carefully in the sky, you would accelerate towards Earth because of Earth's gravity. So you're thinking, but gravitational field strength is measured in newtons per kilogram, Lara, and I've learned that acceleration is measured in meters per second. Yes, we might, it's interesting, and we might, when we do a maths lesson, go into how meters per second and newtons per kilogram are sort of equivalent. But we won't do that today. You're just going to have to accept that another way of describing gravitational field strength is acceleration due to gravity. Right, let's do a quick practical. Have you got a lid of just something in the fridge? It just needs to be something heavy, like a key. And have you got a piece of paper? Any paper, ideally scrap paper. If you drop them, hopefully you can do it with me. If you drop them at the same time, which one is going to hit the ground first? Which one will fall fastest and why? The lid or the paper? If dropped at the same height, which one will fall fastest and why? Okay, let's do it. I've got a good angle here. It was pleasing me yesterday. I've got very, very Blue Peter angle. Look. There. Okay, lid, paper, drop them at the same time. Ah, the lid fell first. But why? Well, some of you might have said because the lid is heavier, right? So that's true, isn't it? The lid has more weight. So you might have said because the lid has more weight, it's been pulled down to Earth with more force, yeah? Like it weighs, 2 newtons instead of half a newton. So more force, pulling it down more, right? Well, let's scrunch up the bit of paper now. This has gone less Blue Peter now, it's less professional. Scrunch up the bit of paper and let's do that again. Are we going to see the same thing or are we going to see a different thing? So we've scrunched up the paper. Is the mass of the paper the same? Yes, it is, isn't it? Is the weight of the paper the same? Yeah, the shape of something doesn't affect its weight or its mass, does it? So it's the same heaviness as it was before. What do you reckon? Which one's going to fall first? Same as before? Lid fall first? Paper fall first at the same time? Let's see. You ready? Oh, it's so good, isn't it? It's so simple, but it's so good. They are both falling at the same speed. and hitting the floor at the same time. So, if you said that the lid would fall first because it was heavier, hopefully now you're thinking, oh, that can't be right, because anyway, this is what we're going to talk about. First of all, we'll deal with kind of the more simple example of free fall. If something is free falling, it's a very good song about free falling. I might break into Free Falling later by Tom Petty. Excellent song. If something is free falling, it means that only gravity is acting on it. No other forces are acting on it. So we've been talking about air resistance a lot, right? So usually, like if something's falling through the sky, there are air particles in its way and the air particles whack into it as it falls. In a free falling situation, there is no air resistance. There's no forces acting on the thing apart from gravity. I have you a sheet here with some pictures of teddy bears and kittens on it to test your understanding of what I've just said. Here we are. So, so confident am I in how tricksy my questions are, I've even written the answer at the top. Something in free fall is only being acted on by the force of gravity. There are no air particles pushing against it, no air resistance. Are these things in free fall, please? An elephant falling to Earth from space where there are no air particles. Is that elephant in free fall? A monkey parachuting through the air. Free fall. A kitten falling through the air with no parachute. A teddy falling above Earth's atmosphere where there are no air particles, but you whack it upwards with a tennis racket every 5 seconds. The moon. Your birthday gift falling to Earth from space where there are no air particles, but it has got a parachute on. Okay, let's go through it. This elephant falling to Earth from space where there are no air particles. There's no air particles. But it is, so you might say, oh, well, in space, there's no gravity. There is, actually. And it's falling to Earth, so it must be experiencing Earth's gravity. So well done if you said that that elephant is free falling, yes, it's free falling. I'm definitely going to get muted if I'm not careful. A monkey parachuting through the air. Well, the air was the clue there. There's definitely not in free fall. No, air resistance will be pushing up against the parachute. A kitten falling through the air with no parachute. But there's still air particles there. So air particles, not as many air particles as pushing up on the parachute, but that kitten has still got air resistance acting against it, so it's not in free fall. This teddy, well, there's no air particles, right? So surely it's in free fall, but if you're whacking it upwards, that's definitely a force. So the answer to that one was, it's in free fall, except while you're whacking it. Well done if you got that. The moon. Let's talk about the moon, people. So what forces are acting on the moon, right? Here's my sellotape Earth, and here's my mustard lid moon. Well, obviously the moon is going around Earth because of Earth's gravity, yeah? The Earth's gravity is attracted, or that's why the moon is orbiting, we know this. Are there any other forces acting on the moon? Well, it's in space, so there's no air particles pushing against it. No, so the moon is indeed free falling around the Earth. Good fact, eh? It's like constantly falling towards Earth, but missing it. That's what the moon's doing. And your birthday gift falling to Earth from space where there are no air particles. Well, there's no air particles, so it's free falling. It's got a parachute on, but I've put, well, so what? The teddy's got a bow tie on. It's still free falling. A parachute is just an annoying thing attached to it, isn't it? If there's no air particles, there's no point to it. So yes, well done if you said that the present was free falling. 2 definitions of mass. Let's spin you around and go into this in a bit more detail. So we looked at how, at this level at IGCSE, mass means how much stuff is in a thing. But that's not the proper definition of mass. The proper definition of mass is how difficult it is to move something. Like how hard it is to move something, I suppose, yeah. Which is a much more useful definition for what I'm about to talk about. So I need to tell you a really amazing fact about things that are free-falling. In order to do that, we just need to, I know it's probably a bit patronising, but I just want to talk about what these equations actually mean. So I've got my simplest example that I always go to when I need to think about how things are divided. The number of sweets per person equals the amount of sweets you have divided by the amount of people that you have, yeah? So the more sweets you have, the more sweets everyone gets, obviously, each. And the more people you have, the fewer sweets each person gets, right? So in maths, I know you're all at different levels here, you would say that the number of sweets and the number of sweets per person are directly proportional. So when the sweets number goes up, this number goes up as well. And the number of people and the number of sweets per person are inversely proportional. If this bottom number goes up, then this number here on the other side goes down, all right? And it's the same over here. Let's look at this acceleration due to gravity. So how fast something falls to Earth, how much it is accelerating, if its weight goes up, then it accelerates more, right? So that's what we looked at with the mustard lid, yeah? We were saying, oh, okay, that most people were thinking the more weight something has, the faster it will accelerate. But look, the more mass something has, the slower it will accelerate, yeah? Because mass means how hard it is for something to move. You don't need to know this. This is just me explaining the cool fact that I'm about to tell you because I think it'll make it easy for you to understand. So in a free fall situation where there are no air particles acting, right, you would think, let's say this mustard lid is in space. Well, let's say it's on the moon, okay? There's no air particles on the moon. Let's say you drop this mustard lid and this bit of paper on the moon. A big bit of paper, like this. You drop the mustard lid and the big bit of paper on the moon, which one's going to fall first? You'd think it would be the mustard lid because it weighs more, so it's going to accelerate more. But it also has more mass, right? So because it has more mass, it's actually harder to move. What I'm trying to tell you is these two things end up balancing out. And on the moon, they would both accelerate the same. And because humans are amazing, they've actually done this on the moon to prove it to people. I'll show you. Look, this is a YouTube video that you absolutely must watch after this lesson. I couldn't show the YouTube video, so I've just taken some terrible quality stills to try and inspire you to watch the YouTube video later, okay? So on the Apollo 15 mission of 1971, Commander David Scott stood on the moon, God bless him, and dropped a hammer and a feather at the same time. It's not a very good quality image, but he's on the moon, and it's 1971. Here's the hammer you can just about make out, and there's the feather in his other hand. So yeah, what happened? Well, exactly what I just told you happens. There's the feather. He's dropped them now. It's much clearer, obviously, on the video. But you can see that they're falling at the same time, and they do indeed land on the ground at the same time. I was watching this video to sort of get the link and set it up for you guys, and you have to watch it because there's this beautiful bit at the very beginning where the people who are chatting in the background, one of them says, like, oh, you need to, have you noted down the solar wind yet? And his mate says, oh, no, I'll do it in a minute. I just want to watch this. It's just, and you can hear in the astronaut's voice how excited he is that they've both landed at the same time. Like, just such a beautiful example of how professional rocket science don't stop being excited about the stuff that we're learning about today. Yeah, it's just amazing. All right, so that is super weird, but it's true that where there's no air resistance, things accelerate at the same speed. Let's talk about air resistance then, okay? Let's do another practical. I said to bring a sort of tall water vessel. So I've got this old ketchup bottle. A pint glass would do if you want to just quickly fill a pint glass with water, but the taller it is, the better. And some grains of rice. So we're going to drop the grains of rice. Don't do it yet. We're going to drop the grains of rice into the water. And I want you to think about what happens once the grain of rice is in the water. Is it going to get faster and faster and faster and faster as it hits the bottom, as things would on the moon? Is it going to slow down, or is it going to travel at the same speed? I've written the question down for you. Sometimes it's easier to think when you can see it in writing. Predict. Will a grain of rice falling through water fall at a constant speed, or get faster and faster, or move more and more slowly? Look, I even drew a diagram. What do you reckon? We're not going to do it. First of all, I'm going to tell you about, the entire point of this lesson. I'm going to tell you about terminal velocity. I made a really weak PowerPoint, a very, very poor PowerPoint, but by the time I realised it was going to be poor, I'd done too much work on it. So, sorry, not sorry. You're just going to have to watch this really poor PowerPoint. Picture a parachutist falling out of a plane. This bit's quite good. There you go. Hey. Okay, so there he is. Their weight is acting downwards, obviously. Like you always have weight if you're in a gravitational field. But the second they start falling, there isn't really any air resistance. There's not many air particles pushing up against them. So this would be the force diagram for a parachutist that had just started falling out of a plane, okay? We've really just got weight acting downwards and nothing above. So have a look at this diagram. This is obviously an unbalanced diagram, right? There's a very big resultant force in the downwards direction. So they're accelerating. They get faster and faster and faster. What happens as they get faster and faster and faster? Well, and there you go. Let's just do it. I won't tell you. I'll show you. Take your hand and very gently touch it against a surface around you, like a table or a wall. So your hand has the same mass, right, every time. You're accelerating the hand, like it's going from still to moving. You're accelerating your hand towards the wall or the table, and the wall or the table is pushing back, right? So now push a bit harder. What happens? Ow! The harder you push, the more force, right? The faster your hand is traveling, the more force you feel. That's what happens to the air particles that the parachutist is falling through, okay? We talk about air resistance, but we need to think about what that actually means. Parachutist is moving through particles of air. The faster the parachutist falls, and it's falling faster and faster and faster and faster because acceleration, right? That means getting faster. So the parachutist comes out of a plane, starts moving faster and faster and faster, and so the air particles that they're whacking into whack against them harder and harder and harder and harder. Is that okay? So when he first starts falling, he'd be experiencing this, and then as he's getting faster further down, he'd be experiencing this. Right, enough, just that. Go back to the PowerPoint. All right, so this guy's accelerating, getting faster and faster and faster and faster. As they get faster, the air particles push against them with more and more and more force. This is what is called air resistance. So the simple way of saying it is air resistance increases. So here's a diagram. We've still got weight acting down, not to scale, is it? That's bad. It should be the same amount of weight, but now we've got a bit of air resistance. So air resistance builds up and up and up, okay? Because they're getting faster and faster and faster. They're smacking into the air particles with higher and higher speed. So then what happens? This is the really, really golden bit of the PowerPoint. So this is what happens first, just weight acting. So they are accelerating, they're getting faster and faster, but they sort of start off slower. Air resistance builds up, okay? So here we are, still falling. Air resistance builds up even more. There we go. Air resistance builds up until, look, what's this? We've got a balanced force diagram here. So what has happened to their speed? It's so clear from my PowerPoint. Eventually, the air resistance pushing back becomes equal to their weight. Is that okay? They travel faster and faster and faster. Air particles push against them more and more and more and more until the air resistance equals their weight. So we've got a balanced force diagram here. We've got no resultant force acting. What do we know about things that are moving when all the forces acting on them are balanced, when there's zero resultant force? They fall at a constant speed, don't they? They move at a constant speed, and that constant speed is called terminal velocity. Hey, we got there. It wasn't too bad a PowerPoint, was it? You might be thinking from that, like, oh yeah, I totally get it. I thought I got it too. And then I started asking more and more questions, and it got more and more confusing. Like I say, I'll link you to some very, very good animations that you can watch, so that you can check that you've really understood it. Right, let's sprinkle these grains of rice into this water now, shall we? And see what happens. What are you predicting now? Is your prediction changed based on what I just told you about air resistance? So obviously, this is not air, is it? We're now putting things through water, but it's just the same thing. It'll behave in the same way. Here we go. So, there goes my rice. What do you think? Falling at a constant speed, right? Yeah? It's reached terminal velocity, hasn't it? I would say. When it first goes in, I mean, there's probably acceleration, but we can't really see it. When it first goes in, the water particles start pushing against the rice, and very quickly, the push of the water is equal to the rice's weight. So it falls at a constant speed. I didn't tell you to bring this because I thought your adults might be cross with me, but I've got some olive oil here. I'm an adult, I can do what I like. I'm going to drop some grains of rice into this brand new, quite expensive bottle of olive oil. Are we going to see the same thing as we saw with the water, or are we going to see something different? It's a good question, isn't it? Actually answer that. Are we going to see exactly the same thing happen with the water that when I drop rice through oil, or are we going to see something different? Go on, answer. Out loud, so that you can really hear how good your thoughts are, because they might sound great in your head and they might come out all wrong. If we're going to see something different, then what different thing are we going to see? Because the oil is, we've got some great lessons ahead about like viscosity and thickness. The oil is thicker. Let's do it. So I guess like if in our model, you would say sort of more air particles, wouldn't you? It might be like falling to Earth on Venus. Wait, falling to Earth? It might be like falling to the surface of Venus instead of falling to the surface of Earth. Yeah, you've got more gas particles in your way. Here we go, let's see. I'll tell you what, I'll put them both next to each other. That's better, isn't it? You ready? Oh, I like how loads more people have tuned in because words got around that Lara's about to pour rice into a jar of olive oil. Right, you ready? Let's do this. Oh, isn't that beautiful? I'm finding this bizarrely relaxing. Look, did you get that? That's definitely terminal velocity, isn't it? They're not speeding up or slowing down, but they're moving ever so slowly. God, I tell you, I could watch this all day. My husband doesn't know about this activity yet. I'm just going to put some more in. Oh. So why are they moving more slowly through the thicker, gloopier liquid? Safe travels, little rice. Why are they moving more slowly through the thick, gloopy liquids? This is the bit that I really had to get my head around, actually. So, something starts falling at its terminal velocity, like doesn't speed up or slow down, when the forces on it are balanced, okay? So something accelerates and, has that dishwasher been on the whole time? I'm so sorry, how annoying. Something accelerates, gets faster and faster and faster, and as soon as the forces on it are balanced, it stops getting faster and faster. So the sooner the forces on it are balanced, the slower its terminal velocity will be. Do you see what I mean? Right? So the water took quite a long time to start pushing against the rice to the point where it was moving at terminal velocity. So it moved faster and faster and faster and faster, and it was eventually going really quite fast before it started to move at a constant speed. Whereas the oil pushed back a lot faster, so it didn't get up to as quick a speed. I'm going to give you the sheet. Here we go. See if you can sort all this out in your head now. I've got you some descriptions, which, if all put together in the right order, will describe terminal velocity very well. So I'd like you to put them in the right order, and then, this is really hard, if you finish it, this is hard because you deserve hardness because you finished, so you should be challenged. I want you to try and fill in these missing gaps to describe what happens when a parachutist opens her parachute. So, a parachutist leaps out of a plane. Put the descriptions of what happens to her in order and draw force diagrams for stages 1, 3 and 5. Apologies if you got the worksheet off Facebook, it will say 1, 3 and 4. It's not, it's stage 5, please. So a parachutist leaps out of a plane, what happens next? Is it until finally the force of the air resistance equals her weight? Is it this speed is called her terminal velocity? Is it as her speed increases, air resistance increases? Another one is, because the forces on her are unbalanced, she accelerates downwards. Another one is, the force of gravity, her weight, pulls her down and there is hardly any air resistance. Another one is, now the forces on her are balanced, so she falls at a constant speed. And the last box just says, and increases. And if you finish, try and fill in the gaps in this paragraph. What happens when she opens a parachute? When the parachute opens, air resistance, space. So the something force is in the upwards direction. The parachutist, something, something. This means air resistance, something. Eventually the air resistance and something balance again, and the parachutist reaches a new something, something, something. Extremely challenging, that one. I am still here. I'm just doing a really unusually good job of being quiet. I'll give you 30 more seconds because I'd love you to have a go at this finished task. It's good brain exercise. Okay, should we get going? A parachutist leaps out of a plane. The next step is the force of gravity, her weight, pulls her down, and there is hardly any air resistance, okay? This must be step one because there's no air resistance yet, and for the rest of the time there will be. So that was step one. So because the forces on her are unbalanced, she accelerates downwards. That was step two. So she's accelerating downwards now, which means speed increasing. So as her speed increases, air resistance increases and increases until finally the force of the air resistance equals her weight. So if the force of the air resistance equals her weight, then obviously the forces on her are balanced, so she falls at constant speed. This speed is called her terminal velocity. Well done if you got that. This one, when the parachute opens, air resistance, the force diagram's right, yeah. So the first one, only weight is acting, so it's just weight acting down. Well done, give yourselves, I don't know, a mark if you got that. Air resistance increases, so you should have done a little arrow pointing upwards because that's the direction air resistance is going in, pushing up. And step 5, the air resistance and the weight are balanced. So 2 arrows of equal length, please, pointing in opposite directions to get a mark there. Okay, now for the fun bit. When the parachute opens, air resistance increases. I mean, you probably knew that, right? When the parachute opens, air resistance increases. That's why the bit of paper that wasn't scrunched up fell more slowly than the piece of paper that was scrunched up, because the wide piece of paper had more air particles acting against it. I guess we can talk about this in terms of the force diagrams that we've been drawing before, right? So if you've got a parachute, what is actually happening? You've just got loads and loads and loads and loads and loads of tiny little air particles pushing up on the parachute. But what have we learned when we were looking at resultant forces? It's that if there's loads of forces on something all acting in the same direction, you can add them up, can't you? So it's just loads and loads of teeny tiny little arrows, but you add them all together, and that equals one extremely big air resistance. So when the parachute first opens, the air resistance is suddenly greater than the weight. So what happens? Well, the resultant force acting on the parachutist now, remember we did resultant force? It's like this sort of length of arrow cancels out this bit, and the overall resultant force is in the upwards direction now. Can you see that? On average, there's more force going upwards. So let's complete this paragraph. So the resultant force, it's all right if you said like average force or overall force, is in the upwards direction. The parachutist, well, what happens if suddenly something's falling downwards, but then the resultant force is going upwards? They slow down. And what happens if the parachutist slows down? Air resistance decreases. This is well confusing me, but it does make sense, doesn't it? Suddenly, resultant force is upwards, so it's decelerating, slowing down, and it comes back to this again, right? If something's slowing down, then the air particles are pushing down on it with less force. I'm telling you, like literally just 10 minutes solid staring at sentences on these websites thinking, what? Yeah, so the parachutist is opened, the parachutist is slowed down, so the air particles are bashing against the parachute with less force, so air resistance decreases. So eventually air resistance decreases and decreases until the air resistance and the weight are balanced again, and the parachutist reaches a new, slower terminal velocity. Ah, we got there. Whew, I love this stuff, but it does do my head in. Right, at this point in the Facebook lessons, the other day, I just launched into a really hard past IGCSE question, and it felt a little bit brain melting. It didn't feel right. So instead, I've got 5 multiple choice questions, which are still quite brain melting, but it's just an easier format, isn't it? So now I've hovered on that for long enough. Let's do some multiple choice questions to check your understanding. And then if anyone really wants to, and your brain hasn't melted, I can go through the super hard IGCSE lesson. This is like the end of the lesson, okay? Right, are you ready? You ready? Deep breath in. Think about everything that you've learned today. Question 1. Which of these are in free fall? Which of these are in free fall? A ball kicked out of an aeroplane, a dog floating through space where no force of gravity acts, Mars, none of the above, or just B and C, just the dog floating through space where no force of gravity acts, and Mars. Isn't that a brilliant question? I can't even remember the answer. I'm going to have to read it myself. Which is in free fall? A ball falling out of an aeroplane, a dog floating through space where no force of gravity acts, Mars, none of them, or just the dog and Mars? The answer is 5, 4, 3, 2, 1. C, just Mars. Obviously the thing falling out of the aeroplane has got air resistance acting against it. The dog was sort of a trick question because there's no gravity acting on it either. Very unusual to get that situation, but if there's no gravity acting on it, it's not in free fall. But Mars is in free fall around the sun because only the force of the sun's gravity is acting on Mars. Well done if you got that. In a place where no gravity is acting, this weird mysterious place, in a place where no gravity is acting, if you drop a hammer and a feather, they fall at the same speed. The hammer falls first, or they both float. In a place where no gravity is acting, if you drop a hammer and a feather at the same time, they fall at the same speed, the hammer falls first, or they both float. 5, 4, 3, 2, 1. The answer is another trick question. They would both float. If there was no gravity acting, they wouldn't fall at all. They would float. Well done. Something reaches terminal velocity when air resistance is greater than weight, air resistance and weight are equal, all the forces acting on it are equal, or both B and C. Something reaches terminal velocity when A, air resistance is greater than its weight, B, the air resistance and the weight are equal, C, all the forces acting on it are equal, or D, both B and C. 5. They're good, aren't they? You think, oh, multiple choice, it's going to be easy. 5, 4, 3, 2, 1. The answer is D. It's B and C. So basically, like air resistance and weight are equal or no resultant force. Well done if you got that. That was hard. Even I'm looking at it like, is that right? Yeah, pretty sure it's right. A planet has a very strong gravitational field, but no atmosphere. No atmosphere, right? No gas particles. If you drop a hammer and a feather, do they fall at the same speed? Does the hammer fall first, or do they both float? On a planet with a very, very strong gravitational field and no atmosphere, do a feather and a hammer fall at the same speed? Does the hammer fall first, or do they both float? 5, a 4, a 3, a 2, a 1. They fall at the same speed. Yeah, they'd fall faster, they'd accelerate faster than on the moon, where there isn't very much gravity, but yes, they would still fall at the same speed because they're in free fall, right? There's no air particles acting on them. And last question. As an object's speed increases, the air resistance acting against it, is it A, increases, B, decreases, or C, stays the same? As an object's speed increases, does the air resistance acting on it increase, decrease, or stay the same? 5, 4, 3, 2, and 1. The answer is increases. As an object's speed increases, the air resistance acting against it increases. Oh, very well done, you lot. I will tell you about how I actually earn money, and then at the end I'll go through this hard question because I've told you about it now, so I have to. All right, you lot. If you would like to support me, if you are enjoying these, if you are using me as a resource, then you can pay me £5 or £6 a month. I mean, you can pay me 10 if you like, but I'd say £5 or £6 a month from the people who are watching is enough for this to be my actual job. So if you would like to pay me £5 or £6 a month, then the link is in the About section on YouTube. In my About section, the About tab takes you to this website called Coffee, where you can sign up for £5 or £6 a month. And not only is that enough to make this my job, but I'll also send you really nice things. I'll send you Theatre of Science magazine. In fact, if you're watching live, when you sign up to support me, you always get the latest issue of Theatre of Science magazine, which is technically now this one on time because it just arrived. I'm posting it out in the next couple of days. It's got a beautiful sundial on it. It's got a beautiful comic that my husband illustrated about a woman who sold time in the 1900s. It's got an article about Einstein's theories. It's beautiful. I'm very proud of Theatre of Science magazine. But because that's only just the latest issue, if you sign up today or tomorrow, I will also send you the previous latest issue because it was a bumper summit issue on seeds, and it seems a bit unfair that you just missed out on it because it's really good. It's got just more activities than usual, it's a bit longer than usual, and it comes with lots of delightful little free gifts. So if you sign up today or tomorrow, I'll send you this with all the free things, and then I'll send you this. And I'll send you some rainbow glasses. All right. Let's go through this this tasty and difficult IGCSE question then. I loved this. So clever. Here we go. Oops, yes. Right. A child lets go of a helium balloon. The upwards force acting on the balloon is 5 newtons. The balloon's weight is 1 newton. Describe how the speed, acceleration and forces acting on the balloon change in the minute after the child lets go. Come on. Don't worry too much about the numbers. Doesn't really matter about the 5 newtons or the 1 newton. Just know that the balloon's weight is not very much, and the upwards force acting on the balloon, the up thrust, is a lot. How are the speed and the acceleration, the forces on that balloon, going to change? So clever. I'm going to give you certainly less than a minute to think about it, and then I'll go through it on the board. So I've got another lesson starting in 15 minutes. I enjoyed myself too much this lesson. I hope you're actually really thinking about it. This is excellent brain exercise opportunity. Don't waste it by just waiting for the right answer, yeah? Okay, so what I love about this question is that it's a terminal velocity question, right? And you've revised terminal velocity really carefully for your IGCSE, and all you've learned is about stuff falling, right? Because that's what terminal velocity means. And suddenly, they send you something like this. Amazing. So the balloon doesn't weigh very much at all. How much does the balloon weigh? It's tiny. But the upwards force on it is a lot, right? It's full of helium, it's moving upwards. So what happens when the kid lets go? Well, it's just the opposite of what we've been talking about, isn't it? There's air particles above the balloon, and the balloon, look, there's an unbalanced force acting on it. So as soon as you let go of this helium balloon, it's going to accelerate, yeah? It's going to accelerate in the upwards direction. It can't be travelling at a constant speed because it's an unbalanced force diagram. So it accelerates upwards. It gets faster and faster and faster upwards. There's air particles above it. So what happens is, when you just let go of it, it's bashing against the air particles like this. But higher up, as it's got faster, it's bashing against the air particles like this, okay? So what happens is, air resistance builds up, but what direction is air resistance acting in? I was just about to do this, but it's not. Because it's not falling, it's going up. So the air resistance is pushing in the downwards direction. So what happens is, so the weight obviously always stays the same, doesn't it? And the up thrust always stays the same, yeah? Because it's still got the same amount of helium in it. So this arrow is always going to be the same. But there's another force acting downwards, this force of the air particles. So that happens. And that air resistance is the one that gets higher, greater and greater and greater. Until eventually, right, yeah, you know, the air resistance equals the up thrust. Oh, not the weight this time, but the force in the upwards direction, the up thrust, is equal to the air resistance pushing back. So we get terminal velocity. So if you wanted like 3 or 4 marks You would have to say that the balloon gets faster. I'm writing backwards, it's YouTube, I don't have to. Huzzah. You would have to say that it gets faster. And so because it gets faster, air resistance increases. I think actually they call it drag in the mark scheme, but but you got away with air resistance. Air resistance increases. It moves faster, so the air resistance on it increases, and then the forces balance. So it travels at a constant speed. And what's the name of that constant speed? Terminal velocity. There. Good question though, isn't it? It's just a good example of how and why you shouldn't panic in exams. Just calm down. You've learned it. They're just giving it to you in a different way to really check that you understood it. It's very smart. I can't argue with that. Okay, that is the end of the lesson, you lot. Thank you so much for coming. Thank you so much for coming, or for watching this back. I think we're going to do forces and motion up pretty much perfectly up until Christmas. And then after the Christmas holidays, we'll start a whole new topic. Okay, thank you so much for coming once again. I'll see you soon. Bye.